In this lesson, we will be solving systems of linear equations in 3 variables and solving real-world problems using systems of linear equations in 3 variables. How can you determine the type of medals the U.S. Olympians won? At the 2000 Summer Olympics in Sydney, Australia, the United States won 97 medals. They won 6 more gold medals than bronze and 8 fewer silver medals than bronze. You can write and solve a system of 3 linear equations to determine how many of each type of medal the U.S. Olympians won. Let G represent the number of gold medals, S represent the number of silver medals, and B represent the number of bronze medals. The system of equations above has 3 variables. The graph of an equation in 3 variables, all in the first power, is a plane. The solution of a system of 3 equations in 3 variables can have one solution like that one did, or, which is lovely, or infinitely many solutions because planes intersect in a line, or there could be no solution. Okay, so planes could cross, I don't know, what do you call that, a tent? Or, I don't know, or never at all. I like never at all. That's okay. So there are different configurations where we can have no one point that works for everything. Most of the ones we have will be like this. Solving systems of equations in 3 variables is similar to solving systems of equations in 2 variables. Use the strategies of substitution and elimination. The solution of a system of equations in 3 variables, x, y, and z, is called an ordered triple and is written as x, y, z. Solve. Okay, good directions. We want to eliminate one of the variables first of all, so we're only working in 2. And I can see that the first equation and the last equation both have a 2z, and it'd be easy to take the second equation times 2 and get a negative 2z, so we can get our z's to all drop out. Okay, so I'm going to multiply that second equation times 2. To save some video time, I went ahead and copied the first equation down with that one under it, and copied the third equation down with that one that we'd multiplied by 2 under it. Now we can add, and our z's are going to drop out, so I have 9x plus 5y equals 12, and 5x plus 6y, negative 2z plus 2z is 0, equals 26. Now we can use any of our substitution elimination tools that we already have. I think I'm going to eliminate the y's next. Why not? I'm going to take that equation times 6 and this one times negative 5. And you want to be careful, use a calculator on the arithmetic. Yeah, check that out, 12 times 6. I was pretty confident on that one, 72. The 26 times negative 5, I definitely use a calculator. So we're going to add straight down. 54 minus 25 is 29. My y's are gone. 72 minus 130 is negative 58, which makes me happy, because when I divide both sides by 29, I get x equals negative 2. Now we can take that negative 2 and substitute back into either of those 2 equations we had for that step. And I just picked the one on the right because it was next to it. So 5 times negative 2 is negative 10. Add 10 to both sides. 6y equals 36. So y is 6. And now to get z, we need to go back into one of the original equations. And I'm going to use the first one. Why not? 5 times x we found was negative 2, plus 3 times y we found was 6, plus 2z equals 2. So I've got negative 10 plus 18 plus 2z equals 2. So 8 plus 2z equals 2. Subtract 8 from both sides, and 2z equals negative 6. Divide by 2, and z equals negative 3. Kind of using that Olympic theme here, a little red, white, and blue. Okay, so we had x is negative 2, y is 6, and z is negative 3. Now I want to check it in the other equations to make sure it works there as well. In the second equation, we've got negative 4 plus 6 minus negative 3. So plus 3, I hope, equals 5. Negative 4 plus 6 is 2, plus 3 does equal 5. And negative 2 plus 24 minus 6, we hope, equals 16. And 22 minus 6 is 16. So it works in all three equations. I know I'm right. And I'm not going to write down the check step for you every time. I just thought it was worth doing once. Okay, we're solving again. And this time I think I might want to drop out. Should we drop out the y's first? I'm going to use that first equation, and I'm going to multiply it by, first I'm going to multiply it by negative 2, and then I'm going to multiply it by negative 3. Because then that's going to give me opposites for the y's. If I copy down the second equation now, x plus 2y minus 4z equals 7. And the third equation here, 6x plus 3y minus 9z equals 15. This is lovely. When we add, I've got negative 3x, no y's, plus 2z equals negative 3. But Houston, we have a problem here. When I add, I get no x's, no y's, no z's. I get 0 equals 0. Well, 0 does in fact equal 0. That is a true statement. So this is going to be our infinitely many case. All the variables drop out and you get a true statement. There are an infinite number of solutions. This time, let's eliminate x out of the first two equations. So I'm going to take the first equation times negative 2. So we've got negative 6x plus 2y, that was a negative 2, plus 4z equals negative 8, and copy down the second equation. And add straight down, my x's are gone. I've got 6y plus 12z equals 3. And then if I take the first equation times negative 3, I get negative 9x plus 3y plus 6z equals negative 12. Add straight down, the x's drop out, so we've got 9y plus 18z equals negative 15. Let's get the y to drop out next and solve for z first for a change. Sure, why not? So we'll take the first one times negative 3. And the second equation times 2. And add straight down. Uh-oh. My y's and z's both dropped out. I get 0 equals negative 39, which I'm pretty sure it does not. So that's the opposite of infinitely many. That's our no solution scenario. There are 49,000 seats in a sports stadium. Tickets for the seats in the upper level sell for $25. The ones in the middle level cost $30. The ones in the bottom level are $35 each. The number of seats in the middle and bottom levels together equals the number of seats in the upper level. When all the seats are sold for an event, the total revenue is $1,419,500. How many seats are there in each level? It makes sense to let U be the number of seats in the upper level, M for the middle level, and B for the bottom level. So then the first sentence, the total number of seats, U plus M plus B, is 49,000. And then the next sentence gives us the cost. So we've got 25 times the number of upper seats, plus 30 times the number of middle seats, plus 35 times the number of bottom seats is a total of, oh, this is going to be a fun number, 1,419,500. And then conveniently, they said the number of seats in the middle and bottom together equals the number of seats in the upper level. Okay, so that's begging us to do a little substitution. If we take that first equation and where there was a u, we're going to replace it with m plus b. And then going on, plus m plus b equals 49,000. We can combine our like terms. We have 2m plus 2b equals 49,000. Yeah, we're going to hold that thought for a second. And we'll go ahead and go to the second equation, and where there was a u, replace that with m plus b. And we distribute the 25. And I'm going to pause this while I copy everything else down. Then we can combine like terms. So 25m plus 30m is 55m. 25b plus 35b would be 60b. And there's our favorite number of all time again. It's kind of long. Okay, I'm looking at that equation that we made up here and thinking, hey, that'd be pretty easy to solve for, say, m, and substitute in. If we divide both sides by 2, we're going to get m equals 24,500 minus b. And we're going to use that to substitute in for m in that equation. So where there was an m, I'm going to replace it with 24,500 minus b and distribute. Next we get a combine like terms, and I'm going to pause again to copy down these long numbers. So negative 55 plus 60 is 5b equals big number again. Subtract 1,347,500 from both sides. Nice. And we get 72,000. Divide by 5. And now I know something. The bottom level has 14,400 seats. Now we can go back to one of those two equations and get m Oh, we have a lovely equation right up here. M equals 24,500 minus b. I rewrote it so we could see it. So all we have to do to get m is take 24,500 minus 14,400. And we get the middle level having 10,100 seats. And all that's left is the upper level, which we know was the sum of the other two. So if we add 14,400 plus the 10,100, we're going to get 24,500 seats. So there won't be a lot of problems on these assignments because one problem takes a bit of time. A system of 3 equations in 3 variables can be solved algebraically by using substitution or elimination method repeatedly until you have everything you need.